My name is Crystal Dilworth. I'm a neuroscientist with a PhD from CalTec in Pasadena, California. It sounds like science fiction. Thin metal electrodes implanted in a human brain, connected to physical wires and able to read and translate the individual activity of neurons as conscious activity is performed. Computers, reading our minds. For paralyzed patients, this technology offers immense hope. But for others, it heralds a new era of brain-machine interfaces. Either way, the future is here.
Powering the future. Confronting the world's challenges with cutting-edge solutions, medical breakthroughs, and high-tech discoveries. These are the stories of our planet. This is VOA Tech.
In a split second while driving a car, Nancy Smith's life was forever changed.
I made a critical error and ran into a truck, which caused me to be paralyzed from my shoulders down. It severed my spinal cord at level 3, 4, and 5. They're fused. So the only movement I have is my head and my shoulders. I'm completely dependent on someone else to take care of me 24 hours a day.
Like Nancy, James Johnson was also severely injured in an accident.
And I was riding a go-kart, and it flipped over after I hit a rock and landed on top of my neck, and it broke my neck.
Today, Nancy and James are quadriplegics, paralyzed and confined to wheelchairs because of severed spinal cords. But that hasn't stopped them from participating in cutting-edge scientific research at the Casa Colina Research Institute in Pomona, California. In fact, they're participating because of their injuries.
Working with my doctor and pleading, find something for me to do. I can't take this, I've been a school teacher for 22 years. I can't just shut down, and stare at the ceiling all day long. My doctor called me and told me about the research here at Casa Colina. And she says, would I be interested in this brain research? I said, is it gonna make me any better? She says, no. I said, all right, well, let's find out about it anyway.
It'll be a great opportunity for me to get in on something that, if it doesn't benefit me, will benefit a lot of other people.
Nancy and James are participants in a brain study at Casa Colina in conjunction with CalTec and UCLA. Here, researchers are studying ways to monitor the brain and to give those who are disabled more function. Dr. Nader Paradian leads the study at Casa Colina and explains a bit of our current understanding of the brain.
So I know that the cells in the brain have sort of two different languages. There's the chemistry and then there's the electronics of it all. And your specialty is electronics of it all. Tell me about how we can interfere with those processes to improve brain function.
So I talk a lot in terms that people tend to understand a little bit more, which is the heart. When the heart becomes sick, it develops an abnormal rhythm. And that's very comprehensible for people because you can hear a rhythm or you can see that your EKG looks abnormal. It turns out we have rhythms in our brains also. And if we put the right sensors in the brain, we can actually listen to those rhythms. Not in the way that you see the heart pumping, but the brain has those rhythms. And we can see that they're abnormal when people have neurological diseases, psychiatric diseases, and even brain injury.
What we're trying to do is basically replace some of the function that's lost in spinal cord injured patients.
Tyson Afalo is the lead researcher at Casa Colina.
In the case of spinal cord injury, people's brains are still intact. They're still able to think about what they want to do. They're still able to experience the world. The only issue is that the connection between their brain and their body has been severed. And so the idea is we can implant electrode arrays to kind of record this useful brain activity about their thinking about what they want and translate that directly into actions in computer interfaces or robotic limbs.
In neuroscience, this is called a brain-machine or brain-computer interface.
I met with everyone here at Casa Colina, Dr. Paradian. They told me where it was going to go in what area, the parietal area of my brain. I looked it up and I said, okay, that's not a bad place to put it. You know, we were going to research the brain and what things were going on in that particular part of the brain, that area. I said, okay, let's go, let's do it.
The parietal lobes of the brain process sensation and perception and visual sensory input. That's only one specialized region of the brain. Within the brain are neurons, 100 billion of them. These brain cells are highways of communication, sending information from one cell to another via an electrochemical relay system. When the system works, so do you.
The kind of core elements of the brain are neurons. So neurons are what kind of process what we want to do and what we experience. And they're really, really small. And so to kind of get at what they're doing, we need to kind of have a fine-grained recording of the human brain. And the best way of doing that we know so far is with these things called electrodes. And so in order to get those electrodes into the human brain, we have to actually implant them surgically. And it's you know, brain surgery. You need to actually pop the skull off, implant the electrodes, put the skull back on, and that gives you the kind of conduit to kind of record brain activity.
Which is exactly the type of brain surgery Dr. Paradian performed on Nancy Smith and James Johnson.
And if I was going to be helpful in that area, I was willing to do it. So we don't know enough about the brain. The brain's the best machine on the planet, but we need to know more about it. And so that's why I signed up. I was fine with the surgery.
Here, in the Casa Colina Research Lab, Tyson Aflalo gives VOA Tech a rare look at how Nancy Smith contributes to the brain study.
So right now, I'm just plugging Nancy in. So actually, if you look over here, you can actually see that there's this grid of electrodes with these little contacts, and each contact hooks up to an electrode that's actually penetrating inside of her brain and is able to pick up electrical signals from her brain. So what we're doing now is we're just creating a pathway for those brain signals to actually reach our computers. Kind of advanced machine learning combined with just hooking up some wires together. So here what we're looking at is each of these contact points. So there's an electrode array that's been implanted in Nancy's brain, and it's this grid of 96 electrodes in a basically 10 by 10 configuration. And so each one of those electrodes, the activity we're recording from them is mapped to this grid. And so each one of these represents what we're recording at an individual electrode. And so what we see, let's say in a particular channel, so we can look here, load this up big, is we can see that on this particular channel, we're recording what they call an action potential. So that's actually the signaling of an individual neuron. And let's see, we can actually hook up each neuron to a speaker, and we can listen to it. And so now you can hear a little bit better what an actual neuron sounds like. So you hear that crackly sound. So that's just the sound that a neuron makes when you just listen to its broadband signal over a speaker.
Take a moment to consider what we're hearing right now. This is the actual sound of a neuron sending electrical signals in a human brain in real time. As Nancy thinks, this neuron is creating its own rhythm.
Each of these neurons is basically telling us something about what Nancy wants or what she's experiencing in the world. And kind of our job is to figure out what they're telling us and to interpret that activity and use it in some way that's useful to the patient.
Why is this so important and why is it new?
So it's important because a lot of what we know about the brain comes from animal research, non-human research, which has been absolutely essential to get us to the point that we're at right now. Without all the work that's been done, we wouldn't have a fraction of the knowledge that we have now about the human brain. But we've been able to use that as a foundation now to go into human subjects or human research participants to really take it to a whole new level.
So the key here will be to understand what causes this neuron to fire more and fire less. And so sometimes it might be related to what Nancy wants to do. And so we do this in a more systematic way. Let's see what happens when you think about squeezing your hand into a fist. So when I say go, squeeze your hand into a fist. Go. Go. And so right now you're just trying to pick out with your ear, does that kind of crackling happen a little more frequently when we actually kind of tell her what to do and she kind of imagines doing it? Another thing might be, we'll see how it responds when she actually sees an action being performed. Reach out and grab the scissors, right? So there we could actually see like a much more brisk response when she watches me grab the scissors. That seems to really drive this neuron. So what it's telling us is that this neuron seems responsive to when she just sees an action being performed, like a grasping action. And so you might try, what about if we kind of grab it in different ways? This is my son's elephant, brought in as a prop. Right, so it really fires briskly to that. Now, Nancy, now imagine reaching out and grabbing the elephant in the same way. So when I say go, imagine reaching out and grasping the elephant. Ready? Go. Go. So sometimes we'll find neurons that fire both when she sees an action being performed as well as when she herself performs the action. So this one seems to be actually more specific for when she sees an action being performed. This is why science is hard. So why does it care more about me grasping this elephant than, you know, pinching my own fingers together or grasping these pliers?
James Johnson had the same surgery as Nancy and is also participating in the Casa Colina brain study.
After my accident, I felt pretty useless, and I went through a heavy depression. Or prior to the surgery for this project, I was concerned that if I would come out on the other end worse off than when I went in. And so that really concerned me.
James did have the surgery, and everything went well. As a participant of the brain study, he meets with Tyson Aflalo at Casa Colina several times a week.
In this study, we are looking at two different parts of the brain that are both thought to be responsible for translating your thoughts into movements. And one area is the posterior parietal cortex. It's an area that receives kind of visual and somatosensory, your body sense information, and translates it to planning activity. So when you think about movement before you execute it, your brain kind of organizes your brain activity to then produce a subsequent movement. And so we're recording signals from this kind of planning area of the brain. And then we're also recording from primary motor cortex. So that's the area of your brain that would normally send signals directly down to your spinal cord to actually translate your thoughts into action. And so the reason for this study is to look at how these two brain areas program movements when the subject thinks about moving things, and how we can kind of utilize those different information sources for a brain-machine interface to allow a subject to use their thoughts to control, you know, computer cursors, robotic limbs. Really anything that would help the patient kind of regain lost function. So we made these little templates just to kind of keep his hair out, both so we don't yank his hair out all the time, and also so we can connect a little easier.
No, it's pretty comfortable. I don't just feel like someone's just tugging on my head a little bit, but it doesn't hurt or anything.
All right, so we just connected. So Dr. Neda Paradian implanted these electrode arrays, these fine little wires that actually penetrate into the brain. And really they're nothing, they're just little electrodes. And those little electrodes are detecting brain activity. And what these do is they actually connect those arrays, those electrodes implanted in the brain, to the rest of our computer equipment. So we can actually detect what his brain is doing while he's doing these tasks. So the first thing we do is we just get a look at what James's neural activity is looking like, make sure the connection is good. So here, it's looking not too bad. So each one of these panels is what we're picking up in an individual electrode. There's a little bit of noise, but what we can see here is pretty clear individual neurons. So every time a neuron in your brain fires, when you detect it on an electrode, it'll make a very characteristic shape as ions go in and out of the cell membrane. And so we can see when a neuron's firing based on those kind of repeatable waveforms. And each one of those waveforms, each one of these neurons is telling us something about what James wants or is experiencing, and we're going to translate that into control of a computer. So we have 2 panels now. Each one is detecting signals from different brain areas. So the one over here is detecting signals from his posterior parietal cortex. It's kind of the back part of the brain. And those are signaling things more about his kind of upcoming plans for when he's going to move and what he's going to do. And this one is from primary motor cortex, and that's signaling kind of the moment to moment. So we're opening up now is a very simple video game environment. And we're going to train our decoding algorithms to be able to properly interpret his brain activity.
So this is him training the computer.
This is him training the computer, that's right. Okay. So first, what we'll see is the computer controlling the actual cursor, and James is going to be pretending as though he's the one that's controlling it. And what that gives us is we can see the patterns of brain activity when James is trying to move, when he's wanting to move. And so let's say right now the cursor is going up. James will be trying to move up, and we'll see there'll be some neurons in the population that will become active for him wanting to move up. Different neurons will become active for when he's wanting to move down or moving to the right. And what we're doing here is we're learning what neurons are responsible for what kinds of actions. And we can use that information to train up a decoding algorithm and then turn control over to James. So now we're going to give James full control over the cursor, and we'll adjust based on this attempted brain control. And we found that normally, so the cursor is going to be moving a little bit slower now, and that's just kind of what we found works well for this kind of parameter, for how we kind of train up this decoding algorithm. And then it'll be much faster once we kind of give him full control and he's ready to go. Yeah, so that's him just pushing that cursor around using his brain.
That's pretty awesome.
Again, let's take a moment to consider what is happening right now in real time. James is thinking about moving his paralyzed fingers to direct the dot on the screen. The dot moves in response because his neurons are informing the connected computer of his intentions. The computer performs the action.
So right now I'm using my thumb. Well, I'm imagining my thumb moving like a joystick around to move the cursor to each landing. And for me, it feels like it's my actual hand moving, even though my hand is not moving. But the sensation is there, and that's how I'm able to control going back, forward, diagonally. And so right now, I could go a lot faster, but the program is not letting me go as fast as I normally would want to at this point. It feels really good because my hands are paralyzed and I can move my arms, but my hands just kind of don't move at all. And so to have this feedback to my brain, it makes me feel like I can have purpose again with my hands. It is very fatiguing. When I first started back in January, just doing this, I would be so tired. I feel like I have to give my hands a rest. And I think it's the same sensation as if you were typing on the keyboard and you get the sensation of carpal tunnel. That's the sensation I get.
Really?
When I'm doing that with my brain.
It's a physical sensation.
It's a physical sensation. So by the end of the day, I'm pooped.
So what is the hope for the research you're doing with Nancy and for James?
We want to fundamentally understand how certain parts of the brain work. Ultimately, the solutions that we have now, where they have devices that are coming through the skin and we need to connect through the skin, that's not going to be a long-term solution. But if we can understand how these parts of the brain work, understand how they decode information, how we can use those to control a computer or control whatever device we want, then we can use that information to design better devices, design technology that's purpose-built for whatever application we're interested in, and eventually, have something that's completely implantable and do the things that we want it to do.
So are neuroprosthetics the future?
I think it is. The future of this work is neuroprosthetics, and it's going to be the marrying of the neuroscience, the neurotechnology, and evolution of society to accept it.
What have you learned about your own brain since participating in this study?
My brain gets tired because I focus and concentrate so much to do the tasks that by the time I leave, my brain is tired. And that it's a muscle that gets tired. But my brain is good. That's what I know about my brain. Well, my hope is that more people with spinal cord injuries would be willing to be involved in research. I would be the odd person that looked online for research opportunities. I'm not sure a lot of people do that. And if those people aren't invited in to be part of a study, we're stuck. We can't move forward. Because there's so many areas of the brain to be studied, so many problems to be understood. We just need more people involved in being willing to have surgery and be a guinea pig.
Do you feel like eventually you can use your brain to fully compensate for what you've lost in your body?
You don't want to go. I really do. I think that this technology could even go beyond spinal cord injury patients. I think of the technologies that are involved in prosthetic limbs. Imagine being able to control a prosthetic limb like as if it's your own, limb, your own arm, to grasp a cup, to pet your dog, to hug somebody that you love. Imagine being able to do that and having that limb respond as if it's always been there, That's where I see this technology going. And I think that we're pushing the envelope far beyond even what it exists today, So in the future, I believe that this will be, it will facilitate those things.
A more seamless integration.
Right.
As neuroscientists and biomedical engineers create new technologies to improve human lives through the interface with machines, Nancy and James's work at Casa Colina is giving the world a glimpse of what is possible and what is yet to come.